Last episode, we watched Shaky inch across a room, a robot that could see, plan, and act. Today, we go backward to the algorithm that made planning possible. Over Christmas, Al Newell and I invented a thinking machine. January 1956, a classroom at Carnegie Tech. Herbert Simon walks in late, doesn't apologize, and drops that line on his students. They laughed. Of course they did. But Simon wasn't joking, and within 2 years, that Christmas breakthrough would become something stranger. A program that claimed to solve any problem you could describe, any problem at all. The Christmas machine Simon bragged about was Logic Theorist. We've met it before. It proved theorems from Principia Mathematica. Impressive, yes, but narrow. Logic Theorist could only do one thing: prove mathematical theorems. Ask it to plan a trip or solve a puzzle. Blank stare. This bothered Newell and Simon, not because they wanted to prove more theorems, because they believed something radical. Problem solving itself was a skill, a general skill. And if that was true, you could program it. By 1957, they had built GPS, General Problem Solver. The name was audacious. The mechanism was elegant. You give GPS a starting state. I'm in Pittsburgh. You give it a goal. I want to be in San Francisco. GPS looks at the gap between them. Then it asks, what operation would reduce that gap? Buy a plane ticket, but to buy a ticket, you need money. New gap. Go to an ATM, but to use an ATM, you need a card. New gap, and so on. This is means-ends analysis. Compare where you are to where you want to be. Find what's different. Apply something that shrinks the difference. Repeat. Simple, almost obvious, but no one had written it down as an algorithm before. GPS proved theorems like Logic Theorist, but it also solved the Tower of Hanoi, that puzzle with disks you move between pegs. It tackled chess endgames, symbolic integration problems. One algorithm, multiple domains, the generality was real. In 1959, Newell and Simon presented GPS at the International Conference on Information Processing in Paris. The AI community paid attention. Here was a machine that didn't just do one clever trick. It seemed to think in a transferable way. But generality has limits, and chess broke them. Chess should have been perfect for GPS. Clear rules, defined goal, checkmate the king, means-ends analysis applies directly. Except chess has too many moves. The branching factor explodes. GPS would start analyzing and then keep analyzing. Hours, days, forever, essentially. The combinatorial explosion killed it. Natural language was worse. GPS needed crisp problem representations. Start state, goal state, operators. Try describing a conversation that way. Try describing why a joke is funny. The problems GPS could handle were what researchers later called well-structured. Puzzles with rules, games with boundaries, the messy, open-ended problems humans face daily. GPS couldn't even begin. According to Dreyfus's 1965 critique, Alchemy and AI, Simon had made bold predictions after GPS's success. A computer would be world chess champion by 1967. It would prove important new mathematical theorems. 1967 came, no chess champion, no groundbreaking proofs. GPS had shown that general problem solving was possible in principle. But the gap between principle and practice was vast. By 1972, Newell and Simon had moved on. Their book, Human Problem Solving, introduced production systems, a new approach. GPS was history. Yet GPS's ideas survived in its children. Strips, developed at Stanford in 1971, powered Shaky the robot's planning. Remember Shaky? The robot that took 2 hours to cross a room? Strips inherited GPS's means-ends logic. Different packaging, same DNA. In the 1980s, Newell helped create SOAR, another descendant. And modern AI planners? They still decompose problems into states and operators. They still look for what's different and what might fix it. GPS failed as a universal solver, but it succeeded as a blueprint. The insight was this: you don't need a special program for every task. You need a general method applied to structured problems. That insight shapes AI research today. Next, John McCarthy needed a language to write AI in. Fortran couldn't handle recursion, so he invented one. 67 years later, it still runs.